Thank you, Professor Du, for organizing this great research forum. Hello, everyone. My name is Jae Kim. I'm an assistant professor in the Department of Chemical Engineering and Materials Science. So today I want to share a little bit of my research perspective and vision with you. It's my great pleasure. The title of my talk is Solid-State Ionics of Energy Storage for Next Generation Lighter, Smaller, and Safer Batteries. Basically, this means that we need better batteries, right? Okay, so let's begin. So I would like to begin with a very short trivia type quiz. So does anyone know who won the Nobel Prize in 2019 in chemistry?
Yeah, who invented the lithium-ion battery from
That's correct.
Texas University.
Yes, right. So the Nobel Prize went to three scientists and engineers who developed lithium-ion batteries. So basically, Nobel Committee recognized their contribution to revolutionize our life by the battery technology. That also means that we are still using the first generation battery systems, lithium-ion battery system up until now. I mean, you have at least one or two of these batteries at home, even at garage if you have a electric car, right? So we had so much benefit from this lithium-ion batteries, but now to look up, for the future, we need a better batteries, and especially for sustainability. So the consumption rate for energy is keep increasing in modern society. To ensure sustainable energy future, we have to implement renewable technology in our power generation. And the bridging between the renewable technology and sustainability, the battery will play a key role because it can remove the intermittency of renewable resources such as wind and solar. I mean, sun doesn't shine every night, right? So we have to have some sort of a storage to make sure we have a full efficiency of renewable resources. Right. And these type of application, right, we need a large scale batteries like megawatt hour scale energy storage. Lithium ion battery technology certainly be a promising candidate for this type of applications, but we still have to consider its resources. So for example, lithium, as you all know, it's not abundant on Earth. Okay, and more to that, the key elements to make lithium-ion batteries is cobalt and nickel, transition metals, and they are very expensive. Compared to that, we know another alkali ion that is earth abundant, that is sodium and also potassium. And advantage of using this system is that we don't have to rely on cobalt and nickel for transition metal. We may be able to use much cheaper manganese iron as our constituent to build the battery technology. Okay, so with these good perspective, why don't we use sodium ion batteries right now? Actually, the history of sodium ion batteries is as old as lithium ion. It's been about 40 years since it first came out, but there is some downside in practice. So what you're seeing here is energy density plot. So top right means you have higher energy density. And as you can see, those area, high energy density materials are all belong to lithium chemistry. And sodium ion batteries tend to have lower energy density compared to lithium in practice. So, so the low energy density of sodium ion battery is, say, one barrier to make this sodium ion battery successful, especially for grid storage. So we want to basically increase the energy density of these type of new chemistries. So to do that, we have to first understand how it operates upon charge and discharge. Okay, so this is basically a simplification. There are lots of complex things going on, but let me show how this works. So we call this a rocking chair type mechanism. Basically, charge carrier for lithium ion, that's lithium ion. For sodium ion batteries, sodium ion, they are charge carriers. Charge carriers move back and forth between electrodes. So for example, upon charging, sodium ion moves from positive to negative electrodes, and to compensate the charge balance, electron will follow, right? And this is energy storage mechanism. Upon charging, so sodium left the material, the positive electrode material, so it leaves vacancy behind in the material, right? So the more you move sodium out of the positive electrode, the more vacancy you're going to generate. So this means that if you charge material completely, that means that your material have now 100% vacancy with some other constituent. Therefore, your structure tends to destabilize. That's why you don't want to overcharge your material. Okay. And then upon discharge, now these ions want to go back to the positive electrode, and this is spontaneous reaction, and electron will flow through the outside of circuit, performing the work, powering your phones and cars, etc. Right. So you see overall picture, right? Ions move back and forth, but structure remains the same. So this is the key, right? We call this intercalation reaction. But this is a simplified picture. Again, when ions move back and forth, it generates vacancy, and vacancy and structure interact. Okay. And this interaction causes some structural relaxation, in which you will see the consequence in following slides. So lithium and sodium ion, it shares the similar structures. You just need to replace lithium to sodium, but in reality, it is not that simple as it sounds. The fundamental difference between lithium and sodium system originates from its size difference. As you know, lithium is pretty small. Lithium ion is about 0.7 angstrom, whereas sodium is much bigger. It has about 30% larger ionic radius than lithium, so it's about 1 angstrom. This leads to a different site preference in the material. So for lithium-ion battery material, lithium tends to sit in octahedral sites, occasionally in tetrahedral sites. But for sodium ion, sodium is much larger, so it cannot occupy smaller tetrahedral sites. It tends to occupy a prismatic site. And these leads to a very complex phase transition upon charging and discharging. So again, upon charging, meaning that removing sodium, and discharging and inserting sodium back. So you see here, the figure on the right, it's a voltage versus capacity plot. So capacity, basically, if you see this unit, it's a charge per mass. Okay, so the amount of charge you store in the battery. So comparing lithium and sodium, first you see is that lithium-ion battery material has higher operating voltage, okay, and much smoother voltage curve as a function of capacity compared to sodium. So there are two takeaway message. Sodium-ion batteries operates at lower voltage, okay, and also operates at a very complex voltage charge and discharge associated with the structural change. So to make sodium-ion battery better, it's critical to increase the average operation voltage of this cathode materials. So we want to pose this critical question, say, can we charge a sodium-ion battery cathode at higher voltage? Of course, the answer is yes, but it requires a little bit of work. I mean, actually a lot of work. We have to optimize the composition. You have to understand which element to to include how much, and also you have to modify the surface morphology, etc. Right. So here is the one example: sodium, titanium, iron, cobalt, nickel oxide. And you see there are two different tests with two different voltage cutoff. And what we get is actually much higher energy density, about 20% more energy density at higher voltage. So the reason why sodium ion batteries voltage was low and did not charge at high voltage is because, again, if you overcharge the material, it leaves vacancy behind, and that destabilizes the material so that your cell dies quickly. But if you know what you do and then you control the structures, then you can charge your material at high voltage without losing capacity much. So simply yes, the answer is yes, okay, to that question, but only if you understand how the structure evolves as a function of uh, sodium content in the material. The the most, I would say, common method to monitor the structural evolution is X-ray diffraction, but we do this in situ. So basically, it gives you a snapshot of structure upon charge and discharge real time. So you see there are some peaks and showing the position change upon charge and discharge. And by looking at this in situ X-ray diffraction patterns, we can analyze which state of charge we are, and also a structural characterization of this material upon charge and discharge. As you know, X-ray diffraction gives you a long-range information about the material structure, but we do want to know the local environment of the material, especially around the transition metal, because transition metal is the center of the redox reaction, which is critical to store electrons. And that can be done by various techniques such as X-ray absorption spectroscopy, and of course, electron microscopy. And if thermodynamic understanding is required, then we can also do DFT computation along with the electrochemistry. So this is one example of X-ray absorption spectroscopy. So if you're looking at this nickel absorption K edge, you see a absorption edge is shifting as a function of charging. This means that the oxidation state of nickel is changing. And also you see here the bond length. So this is XF's pattern. You see the bond length changes as a function of a charge, meaning that nickel octahedra is distorting and recovering its symmetry upon charge and discharge. So we can understand various information about the structure by using this advanced characterization technique using XAS, usually done at the synchrotron beam lines. Another example of looking at the structure visualization is electron microscopy. So this specific image is obtained from aberration corrected HR STEM image. So what you are seeing here, so these bright spots are transition metal, and the other spot is sodium. So what you're seeing is basically a direct representation of the crystal structure of sodium ion battery material that maintains octahedral symmetry. So basically, I overlay the lattice onto this TM image, and it basically corresponds to this structure one-to-one. This is a fully discharged state. So, pristine material, what happens if material is charged? So this sample is obtained at high state of charge. You see now difference, right? So you still see the same transition metal bright spots, but now you do see two different sodium layers, which indicates that now sodium sits in octahedral sites as well as prismatic sites. So I am particularly proud of this results. This is sort of the first observation of alternating octahedral and prismatic sites in OP2 type setting. So, this is alphanumeric definition is to define how the oxygen layer stacking repeats. But, so, long story short, this is very interesting results to see how a sodium battery phase transforms at high state of charge. Right. With that, right, we by understanding structure and crystal structure, its oxidation state and everything, we were able to deliver a high performance sodium ion battery materials. One of the, I would say, one of the best performing cathode materials to date. And we were able to achieve a relatively high energy density. So, to conclude, we can develop high energy density sodium ion batteries, and it can be be a very great promising materials for a grid storage application. But to do that, we need to understand the structure and property relationship. So I guess that's all I have. I mean, there are some, some complex theory behind it, what makes this material behave such peculiar way. But if you're interested, please feel free to shoot me an email. I'm really happy to discuss about this. So I would like to thank my sponsors and also my group and my collaborators. Thank you.
Thanks much, Jay. Very exciting work. Questions from the audience?
Yeah, I have one. I'm from Colombia. I'm studying chemical engineering. And you mentioned in your work that we should avoid to use transitional metals like cobalt, which are more expensive and have problematics during their extraction. But you didn't show us a different cathode for sodium batteries. So I wonder what kind of different cathodes we could implement for further metal ion batteries to reduce the use of cobalt on it.
Yeah, that's a great question. So if you look at this energy density plot, so this plot is somewhat outdated. It's published in 2015. Okay, but if you see all these sodium battery materials here, many of them actually still contains cobalt. And that's because cobalt is such a magical material. It stabilizes the octahedral layered structure perfectly. So our goal is to stay away from cobalt, okay, and use manganese and iron most of the time, right? But we're getting there, not yet. But our ultimate goal is to utilize manganese and iron, okay? But at this moment, cobalt does, so if you see, let me see, if you see Zane's curve in this plot, right? So cobalt, so here in the small box, this shows the octahedral symmetry of transition metal. Unlike others, so say for example, titanium, iron, and nickel, cobalt pre-edge is pretty stable, meaning that it does not change its symmetry upon charge and discharge, upon oxidation, meaning that this material actually stabilizes the material structure. So without cobalt, then you're going to lose some reversibility. Therefore, so far, cobalt is, I would say, it's one of the material that is needed, but we can minimize the use of cobalt by tuning the composition. So to answer your question, we want to use iron. So, so for example, fully 100% iron, but has its own limit. It cannot fully work reversibly. Okay, so we tend to include other elements such as cobalt and nickel. So far, that's the current status. And if you are stay away from this typical structure, so I didn't mention about the structure of the material. There are various kinds of structures available to store sodium. Okay, these are class of layered material. There are another class called polyanion, And then you don't have to worry about much about the cobalt, but then you're going to lose energy density a little bit because they are heavier than this layered material. So it's not really a simple question. We're still working on it. But long story short, we don't want to use cobalt.
Yeah, thank you, Dr. Kim.
Yeah.
Okay, any other questions from the audience? Okay, Jae, I have a quick question, hopefully also for a quick answer as well.
Yeah.
I think our technological world is still pretty much addicted to lithium batteries, right? Perhaps until your sodium batteries come to the market. So is there anything been done in terms of recycling lithium batteries?
So that's very good question. So lithium is limited, cobalt is really limited. So people are very interested in recycling those elements. But so far, the most focus is on cobalt, not lithium. Because lithium, it's difficult to work with. It's difficult to find the right solvent, etc. So far, people are very interested in, but not actually much on the recycling part. Yeah,
Okay.
but it's a way to go. Yeah,
I see. So it sounds like then there's a cost, both to
basically mining lithium is actually
environment.
cheaper now.
Yeah.
Yeah.
And also to the economy in terms of recycling lithium. Okay, with that, thanks very much, Jae. Truly appreciate it.